So we established that quantum mechanics is important for us to understand chemistry because it describes matter and energy on the atomic scale. So we want to talk about quantum mechanics in a little bit more detail before we start talking about atoms and molecules. So like we mentioned earlier, in quantum mechanics, matter and radiation both exhibit wave-like and particle-like properties. And part of this particle-like properties that radiation exhibits are photons. So we're going to talk about how light consists of both wave and particle properties in this video. But first we need to talk a little bit more about waves. Okay, so one example of a wave that I think is very easy to think about is an ocean wave. And a wave is just a periodic variation of some property. It could be water, like our ocean wave. It could be sound waves, so sound density is varying. Or in this case, we're going to be talking about light. We can have a periodic variation of light. And some important properties of a wave include amplitude. So amplitude is the half of this peak-to-peak height. So imagine that this wave was crossing zero in the middle. The amplitude is the distance from zero to the peak. So we have amplitude, wavelength. Wavelength is just the distance between two of the same points in the wave. So the distance between two peaks is a wavelength. And frequency is just the number of cycles that travel in 1 second. So in this case, we're showing you, this is a figure from the OpenStax textbook. This is 1 second. So here we have 1, 2, 3 cycles in 1 second. So this is 3 hertz. Hertz is just unit of frequency. It just means per second. And this wave, we have 1, 2, 3, 4, 5, 6 wavelengths per second, so 6 hertz. Some other important properties of waves include nodes. So nodes are the number of times it crosses this zero axis, and direction. So waves often, if they're not a standing wave, they often have direction. So they're moving somewhere. So our light might be traveling in a direction, our water is traveling in a specific direction, etc. Okay, so a light wave is the periodic variation of an electric field. So we often refer to light as electromagnetic radiation. So it's this variation of an electric field, which we call light. All right, so some really important things about waves is that there's a reciprocal relationship between frequency and wavelength. So frequency is inversely proportional to wavelength. And here we can see that quite easily, that the smaller our wavelength, the more hertz per second that can be the more cycles per second that can travel, and therefore a higher frequency. So speed is equal to your frequency times your wavelength. And for light, the speed of light is a constant. So we give the speed of light the symbol c, so we'll be using that a lot in this class. And all light, all electromagnetic radiation have the same speed if it's in a vacuum. And that's usually that's usually the assumption that we're going to be making in this class. So the speed of light is 2.9979 times 10 to the 8th meters per second. All right, so there's a lot of different types of electromagnetic radiation depending upon the frequency. So we can have visible light is probably what you think of the most when you think of light, colors, or sunlight. And visible light is actually a very small portion of the electromagnetic spectrum. So on this left-hand side, this is really short wavelengths, very high frequencies. And on this right-hand side, these are very long wavelengths or lower frequencies. So on the end here, we have radio, ultrasounds, microwaves. Visible light is up here, and higher in energy than visible light is this UV lamps that are used in your dental office. I was actually just there today, unfortunately. X-rays are even higher frequency, and along with cosmic rays and PET scans. So there's lots of different types of electromagnetic radiation. So because the speed of light is a constant, like we said, we can use this equation. Speed is equal to frequency times wavelength, and just substitute C in this equation. So I wanted to show you an example. So speaking of dental hygienist, so we're just going to be specifically talking about the X-rays. So the X-rays have a wavelength of 1 angstrom. This is the same as 1 times 10 to the negative 10th meters. So it's just asking, what is the frequency of the X-rays in hertz? And it says, assume the radiation travels at the speed of light, which is 3 times 10 to the 8th meters per second. So we're going to use this equation that the speed is equal to the frequency times the wavelength. And we're going to use the conversion that we know that 1 angstrom is equal to 1 times 10 to the negative 10th meters. So we can rearrange our equation to say that frequency is equal to speed of light divided by wavelength. We just divided lambda on both sides of this equation. And if we plug in the speed of light and our wavelength, we get the speed of light 2.9979 times 10 to the 8th meters per second over 1 times 10 to the negative 10th meters. Meters cancel out, and you're left with 3 times 10 to the 18th hertz. And this is a very reasonable frequency for X-rays. All right, we'll go into wave characteristics in the next video.